chat. We're going to get started in just a minute once we know we're fully live. But happy Tuesday. Yeah. I guess I'll use this time really quickly to plug our Thursday office half hour. Yeah. So just a reminder that on Thursdays at the same time, we are running a little office half hour where you can come and ask any questions that you might have. We had one person last time, so we really got to chat. They got some personal 2 hour or personal half hour to just like ask us whatever questions they had about the data science path and data science curriculum on Codecademy. So if you have questions, even if they're unrelated to this live stream, you should definitely pop on and we'll be happy to answer them, especially if it's a small group. So cool.
Yeah, we're also looking into the Codecademy as a pretty active Discord. And so we're looking into making a channel there, talking with people over there. So if you are on the Codecademy Discord, yeah, we might be over there. We'll probably, we're going to do a couple more of these office hours on Zoom. And then in a few weeks, probably try the Discord.
It'll be fun. Yeah, I'm learning about Discord now. So this is good. All right, I think we can get started. I see some people saying hello in the chat. Always fun to know where you guys are signing in from. So let us know, say hello if you haven't already, and we'll get started.
Cool.
Let's see.
Sophie has a new tool that we'll be using today too, which is fun. We have an iPad that we can do some drawings on.
Yes. All right, I'm gonna actually delete all this. Sorry, I was playing around with this morning, but we'll come back to this in a second. So as a quick recap, what we did last week was we took a look at a simple linear regression model where we had an outcome variable, and then we had a predictor, and that predictor was quantitative. I can actually even pull up exactly what that looked like. Right, so we had height and weight as this kind of dummy example. We were trying to predict weight based off of height as our predictor. And so we fit this line. We talked about what are the components that we need to calculate in order to define what this line looks like. And then we looked a little bit at the assumptions of linear regression, and that was as far as we got in week 1. So in week 2, we're now going to kind of transition to thinking about how we could build more complex models than just this simple line. But in order to get there, we need to talk about how to handle categorical predictors. So you notice right now, right, we can think the idea of drawing a line makes a lot of sense when our predictor is height, our outcome variable is weight. They're both quantitative, and so we have points that are kind of along an axis, and then we can draw a line through them. But what do we do if the predictor variable, so imagine like the variable down here is not a number, it's something like, something
a binary thing.
Binary, or something that even is not binary that has multiple categories. Trying to think like if, we're actually trying to predict the weight of dogs, and we have different breeds of dogs, and we've got some poodles, and we've got some pugs,
chihuahuas, yeah.
Chihuahuas. And so we want to include something about the breed of dog in our model, but that's not a quantitative predictor. So we can't really like organize those categories in any particular order along this axis. Doesn't really make sense necessarily to think of it as a line. Eventually, yeah, sorry.
Well, and interesting because we talked about this in our last stats series where there's almost like 2 scenarios here, right? Where one is unordered, where it's Chihuahua and Poodle and your other dog breed. There's no order associated with those. But then you can also have categorical variables where it is ordered, where I know we said last time, like, a rating of 1 to 10 isn't necessarily the best thing to use, but there's, right, is that true that there's kind of like two different ways of thinking about this, where ordered versus unordered really makes a difference?
Yeah, so if you have an ordered categorical variable and you think that the order matters for predicting your outcome, then yeah, it actually, people do it all the time where they use an ordered categorical variable as a numerical variable, as a numerical predictor. So just like if you have a rating on a scale from 1 to 10, you can put that into your model, right? You can just have the numbers 1 through 10 and treat it like a regular number. And people do that all the time. If it's your outcome variable, you need some different methods, but depending on the circumstance. But yeah, for a predictor variable, you can definitely just put that in normally, like you would height. But if it's a fine line, right? So it's like, what about like seasons of the year? Like that's kind of ordered, but there's not really a smallest and a largest. Do you think that, starting from, if you're looking at the temperature, right? Do you think that it just goes up with the seasons numerically? Like, no, you think it's probably, I don't know. So depending on what you count as number 1 and what you count as number 4.
That also loops where like 4 should also be close to 1.
So it's a fine line, and you have to definitely think about how you're going to code categorical variables. Cool. I see lots of people joining. Sao Paulo, New York City, nice. London, Colombia, super awesome. It's always fun to see people from all over the world here. Cool. So I'm going to jump in. So for today, we're going to be using this kind of made up data set. We'll start with a made up data set, then we'll use a not made up data set. But so this is something that I simulated. We're imagining that we work for a company and we're trying to understand, we want to model the time that people spend on the website. So we want to kind of predict how long is somebody going to spend on our website. And so we collect some data about how many seconds people are spending on the website. We also collect some data about their age and what browser they were using. And in this case, we're going to just pretend like only people with Safari or Chrome are visiting our website. So that's a caveat here. Okay, so eventually what we're going to build up to is a model where we could include both age and browser as predictors. But for right now, in order to understand what's going on in that model, we're going to first think about the model where we just include browser. So what I'm going to do is I'm just going to go ahead and demonstrate that I can fit this model. And then we're going to go back and we're going to talk about what's going on. So let's see. We've got statsmodels.api as SM. So to fit this model, we've got SM dot, I think, hold on, actually, I need to pull the code. OLS from formula. I always forget. .OLS from formula. And then this time our formula is just going to be time in seconds predicted by browser. And our data is called website.
Yeah, and again, I think just stressing that we're using some of these built-in packages, which it takes a little bit of like looking at the documentation. Like, Sophie, I imagine you didn't have, you didn't know this from formula function memorized or anything. And so again, kind of just stressing that the exact code to make this happen isn't really the highlight here.
Yes. Exactly. And I saw you answered this question quickly, but yes, I was talking about dogs as an example of a categorical variable. that you could use to predict weight. In this example, we're going to use a different categorical variable, specifically browser, to predict time in seconds. But just in general today, we're talking about the idea of categorical predictors in a linear regression model. Okay, so I ran this linear regression. I'm just going to press run again so this goes by. And you'll notice that I get some output. So it was able to run. So we can do this. But now we see that instead of getting an intercept and a slope on browser, we're getting this slope on browser t.safari. And so what's going on there? Why are we getting this new variable here? That's what we're going to try to figure out. So to start, I'm going to also demonstrate if I just plot this and I plot website.browser against website time seconds. Actually, I actually get a plot as well, and the plot looks like this. It has Safari on one side with a bunch of dots and Chrome on the other side with a bunch of dots. And what I see here, right, so I should have put, I think if I do sns.scatterplot, then it automatically puts the axes, yeah. So this axis is time in seconds, and then this axis is our browser. So we've got Safari and Chrome. Even though this isn't a number, it's still putting Safari over here and Chrome over here for some reason. And then I can see that these dots are each, so like all the dots in this line are people who were accessing the website using Safari. And this is and each dot represents the amount of time and seconds that they spent on the website. So like this dot is someone who came on the website using Safari and spent about 580 seconds on the website. And this dot is someone who spent over 700 seconds on the website and accessed it using Chrome. Cool. So looking at this, do you think there's a relationship, Alex, between what browser someone is using and how long they're spending on the website?
I mean, it certainly doesn't seem as strong as our last one, right? Comparing it to what we did in the last session where we had, points that looked like they could kind of fall along a line, but obviously not perfect. That looked like a pretty strong relationship. Here, I can kind of imagine drawing a line that maybe is sloping upward a little bit, but the points are going to be pretty far off of that line.
Yeah. So, well, in this case, right, we don't really have, first of all, these aren't numbers, but second of all, right, we don't have any points in here. So there's going to be lots of, and then there's a lot of variation even among these points. So by just drawing a line, it's not like we're explaining that much of this variation. But I would say looking at this, right, these dots tend to be higher than these dots. Like if you had to pick the middle of the Safari dots, it might be somewhere around 400. And then if you had to find the middle of the Chrome dots, it might be somewhere around 500, and maybe a little bit easier to see in a side-by-side box plot. But here we've got Safari. The median is a little below 400. The median for Chrome is a little below 500. And so the middle of these two distributions is kind of different. Like there is some relationship between which browser someone is using and how long they're spending on the website, even though it's not prescriptive. If you are accessing from Chrome, you might spend as few as 250 seconds and as many as over 700. If you're accessing from Safari, you might be spending anywhere in this range as well. But overall, these numbers are smaller than these numbers.
Yeah.
Cool. So this is kind of modeling some of that. So let's
Can we
now,
look at those, or are we about to talk about those two numbers in particular?
we will talk about those numbers in just a second. Yeah.
Cool.
I think one thing that's helpful to know, and this is something that I think will help you if you're thinking about trying to learn other packages as well, is what's happening under the hood when we ran this code. A bunch of things, right? Like our computer is doing some calculations, and there are some steps that happen in the midst of those calculations that we're not seeing. So one thing that's a little bit helpful is to actually break that down a little bit and see one of the middle steps. So I'm going to do that by using this this package called Patsy. So actually, Patsy is a dependency of stats models, and it uses this package in order to fit this model. And so I'm going to just use Patsy directly to show you what that middle step looks like. So using patsy.d matrices, I'm going to actually grab this exact same code that I used with stats models. And I'm going to do return type equals data frame so that we can see this. And actually here, let me run this to see what the output is. So there's actually two different pieces of output. There's a y vector and an x vector. Don't worry too much about that right now, but I'm just going to save them as y and x. And then I'm just going to print out x so that we can take a look at it. Okay, so this is what x looks like. In 2 weeks from now, we're going to talk about this column of ones and why that's there. That has to do with some of the matrix algebra that we're using to calculate the ordinary least squares solution to this regression problem. But I want to point out that we get this same variable that we saw before, and you'll see that it's a bunch of ones and zeros. And the first 5 rows are 1, 0, 1, 0, 1. If we look back at our original data, we've got Safari, Chrome, Safari, Chrome, Safari. What's happening here is we're taking this data and we're recoding it as ones and zeros because it's just a binary variable. There are 2 possible outcomes. And so we're just replacing one of them with a 1 and one of them with a 0. And specifically, we're replacing Safari with a 1 and Chrome with a 0.
And if we weren't binary, if we had multiple variables, would we get 1, 0, 1, 2?
So, no, we won't. We're going to do that in a second. But actually, no, we won't. Because once we have more numbers like 0, 1, 2, then we're really assuming that there's an order, that 0 comes before 1, comes before 2, and we don't want that. So in this case, Safari was coded as a 1, and Chrome was coded as a 0, and that's what this means here. So when it says browser t.safari, it's saying that T it stands for true. So it's saying true that this column is equal to Safari, and it's a 1 if that's true, and it's a 0 otherwise. If you've programmed in other languages, you might know that usually true is coerced to a 1, and then false a 0. So this kind of makes sense with this like true false construct. Cool. So I don't see any questions, so I'm gonna jump over to this picture. So coming back to this picture, I'm realizing now that it's a little bit misleading because in this picture, Safari is over on the left and Chrome is on the right. So in reality, these are switched when we're thinking about this.
I see where that negative might be coming from now, because I was saying, oh, this is probably, if I were to draw a line in this picture, it would probably be going up, right? It would have a positive slope. But if Chrome is actually on the left and Safari is on the right, then I would say, oh, that has a negative slope. And so I'm guessing that's why this negative number is showing up.
Yeah, I think that this is, so here's what I'm going to do to make this a little bit nicer. I wish I had done this ahead of time, but let's see if I can do it quickly here. So if I do website.browser.replace, and then I'm going to replace Safari with one dash Safari, and I'm going to replace Chrome with 0 dash Chrome, and I'll do in place equals true so that I make this replacement in the actual data. Let's see if this works. Cool. And then I bet you, oh, still.
Were you thinking it's like alphabetical?
I was assuming, yeah.
Yeah.
What if I do like a crow? You want
Chrome on the left. So A Chrome and B Safari.
We'll try one more time. It doesn't work. It doesn't work.
Yeah.
Yeah. Why is that? Oh, well. Maybe it's just whichever is first in the list is on the right.
There's obviously ways that we could dig into the scatter plot function to like force the axis to be in a certain order.
Yeah. I wonder if we can just like, well, okay, I'm going to let it go. Okay. So instead, I guess maybe I'll draw a picture. Ooh. This will be fun. Okay. So I'm going to stop share for a second and let me, this is my new technology of the day. Okay. We're gonna get an iPhone, iPad via cable, share. And now, can you guys see that?
Yes, that looks good. Yeah, someone in chat is saying that probably because Safari is coming first, it plots it first. So the order of that data was probably determining it, not the name.
I agree with that. Okay, I have to redraw this picture now because I was drawing this before as a but we've got this sort of picture where we've got some points for Safari, right? And then we've got some points for Chrome. I'm not going to do a good job, right? And what's happening is we're calculating a regression line just as we did before, but that regression line is just connecting the middle of these 2 points. So if we have a point here and we have a point here, sorry, the middle of these 2 sets of points, our regression line is connecting them like this. Now, okay, we had, I wish I could give you guys the side by side of the numbers, but I'll write them. I guess I'll write them over here. So in our model, we had that the intercept, ooh, that's thick. We had that the intercept was equal to like 490. And then we had that that like browser
T dot, what was it? Safari or Chrome? I forget which one was 1 and which one was 0.
T dot Safari equals -99 about. Let's like think about what this corresponds to on our graph. So when it says intercept equals 490, that means that the intercept, the y-intercept, is 490. And remember that the y-intercept is just the same as the point at which our line crosses the y-axis. In this case, the y-axis, right, is the same as where all these points are. Because I don't understand the joke.
Just some anime.
Good. So here, right, remember this 0 was corresponding to Chrome. So the y-intercept is this red point here, and that's our 490, right? That's hitting the y-axis at 490.
So that's where, well, so is that that's the point on Chrome, which is 0, that is 490? Or is it like if I extended so that's different than what I expected. What I expected was, oh, let me extend this line. So, so the line hits the y-axis. And then that's my intercept. But I guess that doesn't really make sense because it's already 0, right?
Yeah, so it's all like kind of semantics of how I plot this. So I'm plotting it with space between this axis and this spot, right? But remember, the y-intercept is where the line crosses the y-axis, and the y-axis is where the x variable is equal to 0. So the y-axis is actually this dotted line.
Right. So really, it's all on top of each other, but just for ease of drawing this so we can see the blue dots and stuff, you've shifted it over a little bit.
Yeah. So if I want to make this like a little bit nicer so that we can all see it, we could, have erased this, and we could think of this as our y-axis, and our points are just kind of along it, right? Like these points that we drew for Chrome are all along what's technically our y-axis, because Chrome, we're making Chrome equal to 0, and our y-axis is where, well, that should be a straight line, but
Right. Yeah, and so that makes sense for our intercept there, where it's 490. The line doesn't really continue to extend, or I guess it does extend to the left, but it's hitting the axis right where, since Chrome is encoded as 0.
Right. Exactly. So our line technically continues on in both directions, but the thing that we care about is that the y-intercept is actually the middle of these blue points that correspond to Chrome. And then we've also got some points over here that correspond to Safari, right? So these are our Safari points. And we need to understand what this number is coming from, or where this number comes into play. And remember that a line has to have a y-intercept and it has to have a slope. And so the slope, remember, is rise over run. So the slope of a line is rise over run. In this case, this line has a positive run. So the run to get from one point to the next, we move over 1 unit. That's a run of 1 unit. And then we have to go down to get to the next point by some distance. This is our rise. And it turns out
we know that's like 3. So I bet if we looked in our data and found the middle of the Safari data, it would be what, 391, right?
Yeah, so we'll do that in just 1 second. But I'm going to just write in here, right? So the rise is equal, in this case, equal to -99. And so our slope is rise over run. It's -99 over 1, or -99.
We have a really good question from Harshdeep of last time we had weight and height. And so it was a little bit like more intuitive to understand what these coefficients are meaning. So his question is, what does this represent in terms of the data? What is 490 with respect to time and browser?
Yeah, so that's a really great question. So in this picture, and we'll show it in the data in just a second, you'll notice that the 490, right, is the middle of all of these blue points. And the blue points are amount of time spent by Chrome users on the website. So the middle is going to end up being the mean time spent on the website by Chrome users. And as we see, right, we can think of this as this -99 as a slope, but because the run between these 2 points is 1, right, like the difference between 0 and 1 is just 1, then it's really just the rise, or the difference in the vertical height of these 2 red dots. And this red dot represents the mean time spent on the website by Safari users. So in other words, this -99 represents the fact that on average, Safari users are spending about 99 seconds less on the website compared to Chrome users. Y-axis is seconds. Yes. Good, good call. So the y-axis is seconds, the x-axis is browser, and we've got our y-intercept, which is mean time for Chrome users of 490. And then we've got our slope, rise over run. Run is 1. So our slope is the rise, and that is this distance. And this is the vertical distance between this point and this point. These 2 points each represent the middle of their respective sets of points, the middle being the mean time spent on the website for each of those points. Okay.
We got another good question from the chat of like, why is the rise negative?
Oh, that's a great question. So this comes back to a little bit of like graphing algebra, right? So rise, so coming back to just like equation of a line and slope. Slope is rise over run. And when we think about slope, we think about to get from one point on a line to the next point on a line, how far over do we have to go and how far vertically do we have to go. When we talk about horizontal and vertical distance, we always think of going to the right as positive and going to the left as negative. And we think of going up as positive and down as negative. So this is a positive sloping line, this top one. For this positive sloping line, to get from one point to another point, our rise is up and our run is over. So our rise is positive and our run is positive. So a positive over a positive is a positive. For this one, to get from one point to the next, our rise is down, right? And then our run is positive. Or we could also think of it as like rise is positive, run is negative. In either case, we've got either a negative over a positive or a positive over a negative over a positive, or a positive over a negative is negative. So the slope is negative because we have to go, right, this point, when we go over 1 unit, positive 1 unit, we have to go down to get to the average safari time. And so the rise is -99, which really just tells us that the average for Safari is less than the average for Chrome.
Cool.
Okay. Exactly. Yes. Okay, now this is nice and pretty. I'm going to stop this share and I'm going to go back to my code. Okay. So now let's go ahead and I'm going to copy this over so you can print it out down here. Run. And then I'm going to also do website.group by browser .mean thing. And then we really just want time seconds. So this gives us the mean time in seconds that people spent on each browser. Go back to our regular. Okay. So we've got 489.7 seconds on Chrome and 390.65 seconds about on Safari on average. And you'll see, right, that this number matches up with our intercept. So that's what we were talking about before. The intercept gives us the average time spent on Chrome. And then this number, we said, gives us the difference in mean time spent on Chrome versus Safari. And it tells us that people are spending less time on Safari. So if we take this number and we subtract this number, basically, add these two together, we get 390.64, this 64717, which is exactly the same as we calculated as the mean time spent on Safari.
I guess, so my question after seeing all of this is, like, all of this follows together. We have those two like yellow points. So that corresponds to the intercept, and then we can find the slope between those 2 points. But I guess my question that kind of like relates back to the very beginning is like, why do we choose the mean, right? We have these 2 columns of points, and we could choose the median, or we could choose, some other metric to find the middle. All of this is coming from, we chose the mean of these 2 points. So why the mean and not something else?
It's a great question. So it turns out, and you can prove this to yourself mathematically, remember that when we fit this model, we're using the ordinary least squares method. which is to say that we're trying to minimize the distance between each point and the line. And so if we draw this line on top, we can think, if I remember correctly, yeah, you can, here, I'm gonna just grab this, but I can explain what I'm doing. So if I replot this, and then on top of it, I just plot the points 0, 390 and 1, 489, it'll plot this line. It's kind of backwards for this example, but we'll just run with it, right? If this is our line, we're fitting this line to minimize the squared distance between all of the points in the line. So to minimize the squared distance between each point and this middle. And it turns out that mathematically, the point that minimizes the distance between all of these points and this middle is the same as the mean. Mean equals.
Yeah. And then again, this line looks different. This is a positive slope. And again, that's because we're actually Chrome is 0, Safari is 1. And so if we could flip those two, if we could put Chrome on the left and Safari on the right, but still connect the two means, then it would look identical to that graph we were just drawing before.
Exactly. Okay. In the interest of time, I'm going to switch over to another example where we use a categorical variable with some more categories. So I'm going to grab this data set from here. This is back to our rentals data set. If you've come to any of these live streams before or done any of the regression or other machine learning stuff on our website, you may have seen this data set before. We're just going to look at a subset of it where we have some information about rental prices in Manhattan, and we have some information about what borough each of those apartments was in Manhattan. And you'll notice that borough has, in this case, there's more than 3 boroughs, but in this data set, we have a column borough that has 3 possible values: Brooklyn, Manhattan, and Queens. And so now we've got one more category. And so all of a sudden, this initial setup no longer works. Okay. So I see there's a question. So this the mean time people spend on the website, or the mean time the web browser loads the website in. For this example, I was using it's not real data, but I was just making up that it was the amount of time people were spending on the website.
But it could be either in theory.
But it could be either. You could have a different data set. Yes. And yes, I see someone commented formula for mean is the same as for average. It's just the same thing. Yeah. Use different names for different things sometimes. Okay. So similar problem, but now we've got 3 categories instead of 2. How are we going to handle this number of categories is the question. So I'm going to actually do the same thing that I did before with patsy.d matrices. I'm going to print out the X matrix for this problem, where we're predicting rent based off of borough. And this time the data is rentals. And
yep, if you like the web browser example, again, this would be the exact same thing if we added a third browser. If we could do predicting time based on Chrome, Safari, or Firefox, or whatever you want.
Exactly. I probably should have done that, but didn't make a new data set. Okay, so you'll notice that now we actually get multiple columns that didn't exist before. Now we get 2 columns of the format borough T something, but now we've got borough T Manhattan and borough T Queens. And then we don't have borough T Brooklyn, even though we know that that's represented in the data set. So let's look through this. We've got our first 5 rows, remember, are Brooklyn, Manhattan, Manhattan, Queens, Queens. So for the T Manhattan column, we've got 0, 1, 1, 0, 0, and we see that that matches up with the 2 rows where the apartment was in Manhattan. So this column is going to be 0 everywhere that the apartment was not in Manhattan, and it's going to be 1 when the apartment is in Manhattan. It doesn't matter if it's not in Manhattan and in Brooklyn or not in Manhattan and in Queens. Either way, it's going to be a 0 if it's not Manhattan and a 1 if it is Manhattan. We call this like a dummy variable for Manhattan. And then for this column, we have the same thing, but for Queens. So it's a 1 if the apartment is in Queens. That's why we have 2 1s here. And it's a 0 everywhere else. So Brooklyn or Manhattan is not Queens. So we're going to get 0s everywhere else. Alex, do you have an idea why we don't need to have Brooklyn here?
Yeah, I guess we can figure that out from kind of process of elimination of if we know there's only 3 categories, and I guess taking that row 0, for example, it's not Manhattan, it's not Queens, and because we know we only have 1 more category, we can kind of deduce the Brooklyn column based on these other 2 columns.
Exactly. So having a separate borough T Brooklyn column doesn't give us any more information. When we get into multiple linear regression, so we have multiple predictors, we'll talk about this issue of collinearity, which means if you have an extra column of your data that provides no new information compared to the other columns that you have, then that actually causes issues with fitting the model. So we've got just the 2 dummy variable columns that we would need in order to fully recreate this borough column. But we have the minimum amount of extra information. Okay. So now let's go ahead and actually run the regression. And we'll see what this looks like. So we've got model equals, and this time we're doing rent predicted by borough. We're printing the model parameters, and we'll see that we get an intercept again. And then as expected, based on this output, we get a slope for T Manhattan, and we get a slope for T Queens. 2 different slopes. What do we do with that?
So I have no clue how to interpret the 2 different slopes, but if I were to do it independently of each other, so the intercept is where it's hit is going to be the mean of the whatever is categorized as a 0, which I guess in this case is well, I guess it could be either of them, right? Like it's not the same thing where we have like it's not 0, 1, 2. So I actually don't know. I was going to guess that 3,000 was the mean of Brooklyn. But I don't know if that's the case or not.
So let's draw it out. I'll switch to, this is so fun. I'll switch to my drawing board again. That should work. Okay. See that? And I'm gonna just write out these numbers again. So we've got intercept. Our intercept was equal to 3327. Our borough T Manhattan was equal to 1181, roughly. And then our borough T Queens was equal to -811. It turns out we have two lines that we've now determined based off of this, this regression output. So this time, in our first graph, we've got a comparison between Brooklyn and Manhattan. So in our Brooklyn versus Manhattan graph, we've got some points for the rental price in Brooklyn, and then we've got some points for the rental price in Manhattan. Again, this y-axis is rental price. And then the middle of those points is going to be, that's our mean rental price in Brooklyn. Here, I'll label these axes. So this axis here is Brooklyn. And then this axis here is Manhattan. We're treating Brooklyn as 0. We're treating Manhattan as 1. And then we've got the mean here. The mean in Brooklyn is equal to the intercept. So the mean in Brooklyn is 3327. And then this is our line, our regression line. And remember, again, since Manhattan is 1, Brooklyn is 0, our run is 1. So the slope is really just the rise. So the slope is the vertical distance between these two. That's our slope. And that's equal to this value. So, Alex, what is the slope borough T Manhattan? What does that represent?
So that represents, yeah, I can figure out the mean of Manhattan based on that, where we're going to be going over 1 unit, and then up 1,100 units. And so I can say, okay, the average of the Manhattan data set is 4,400, 4,500 something.
So let me write that in. So the vertical distance between these 2 points is equal to 1181. And so if the average price in Brooklyn is 3327 and the difference between Brooklyn and Manhattan is 1181, then this point is equal to, or this height is equal to 3327 plus 1181, whatever that is equal to. We'll calculate that in a second. Then we also have this second line, that's determined by this slope, and I'll draw that on a separate axis. So we still have all of these points for Brooklyn. And the mean of those points is still 3327. Well, so the mean is still 3327 for Brooklyn. Right, this is still 0, and it's still Brooklyn is 0. But now we've got 1 over here, which corresponds to Queens. Sorry, I'm still learning how to use this iPad. Right, our 1 corresponds to Queens, and then it looks like the slope is negative. So I'm going to draw these points so that we can visualize it a little bit lower. And then the average is about 811 units lower than this average. So our regression line is like this. And the vertical distance between the points is minus 811, which means to get to this average, the average in Queens, average rent in Queens, we've got to take the intercept, which is the average rent in Brooklyn, or 3327, and we need to subtract 811. So basically all we've done, and I'll go back now to our code. Basically all we've done here is we've recovered the average prices in each of the boroughs. So what I'll do is I'll now do rentals dot group by borough, and then calculate the mean rent.
Sophie, we can't see you typing that for some reason.
Oh, what am I sharing?
Or at least I can't see it.
Let me try.
Yeah, great question in the chat, which we should definitely get to, of why did we not get between Manhattan and Queens? Why was everything based on Brooklyn? But okay, cool, we can see that now.
Yeah, that is a great question. So if we print this out, we see that the average rental price in Brooklyn is 3327.4. So that's this number. Then we see that the average rental price in Manhattan was 5,138. And if we take this, we take this number and we add this number, we should get that number. Nice. And then if we take this number and we add this number, so by adding a negative number, we're just subtracting, but put the plus sign in there, we get the average rental price in Queens. So by giving us the intercept and the 2 slopes, we can recover the rental price in every borough, because this is the average in Brooklyn, and then this is the difference in Brooklyn and Manhattan. So by adding these 2 numbers, we get rental prices in Manhattan. And then this is between the difference between Brooklyn and Queens. So by adding the intercept and this slope, we get the rental price, average rental price in Queens. Okay. So if we wanted to make a different comparison, so remember when we printed this out, Brooklyn was the missing column, right? We had Manhattan and we had Queens. We call in this case, and this is just by default, Brooklyn is the reference variable for this regression that we're doing. And anytime we have a categorical variable with more than 2 categories, we need to choose a reference variable that's going to be omitted from the regression, or omitted from this like design matrix. And in every case, then the intercept is going to give us at least for simple regression, the intercept will give us the average for that group. And then all of the slopes will be in reference to that group. So that's why we call it the reference variable. If we want to change the reference variable, then we can use some other notation. So I'm going to just quickly show, because I already have this written out in here, I think. So this code, this like notation tells this function that I want Manhattan to be the reference variable instead of Brooklyn. If I want Manhattan to be the reference, or if I say Manhattan is the reference variable, then the intercept now represents the average in Manhattan. And then all of these are in reference to that. So now this is Brooklyn compared to Manhattan, and this is Queens compared to Manhattan. And I could choose any reference variable I wanted. If you're using Sklearn, which I know many people do, you have to do this manually. So you can do pd.getDummies, and then if you don't do drop first, so if you like, here, I can port this over. So if I use this get dummies function, it gives me all 3 dummy variables. And then in Sklearn, I can actually just choose which ones I want. So if I want Queens,
just ignore Brooklyn.
The reference variable, I can put in Brooklyn and Manhattan to this model, and then print out the coefficients, and it'll give me everything in reference to Queens. This is the way that this prints out. This is the intercept, and these are the 2 slopes. The Sklearn output is a little bit harder to read.
Yeah. Sophie, I know that we're like basically out of time, but my question is like, how does this all come together, right? Where we now have these 2 graphs, we have these 2 lines, but I don't even know how to visualize plotting the 3 columns of lines of Brooklyn, Manhattan, Queens. Like I don't know how to get all of this onto one graph now.
Yeah, so it would be pretty hard to graph it in one graph. And that's going to be part of the difficulty as we move towards more complicated models with more predictors. Because basically what this is we basically started talking about multiple linear regression without realizing it, because when we fit this model, we actually fit a model with multiple predictors. It kind of happened unintentionally because we had one column in our original data set, but in order to fit the model, we actually had to create an extra variable in order to model this using linear regression. And actually, the same thing is true for most machine learning models that you might use. You're going to have to dummy code categorical variables, because most models use like numerical distance metrics. And if you don't have things written as numbers, then you can't fit the model. So as we move into more complicated models where we want to have, let's say we want to predict rental prices based on borough, number of floors, area, number of bathrooms, number of bedrooms, like we want a lot of things, we're going to end up with this really complex model that we can't really visualize anymore. If we have multiple quantitative predictors, like if we have 2 quantitative predictors, we end up fitting like a plane. So we can kind of visualize it in 3D space. But then once we get past 3D, like 2 predictors, we're stuck. We can't visualize things anymore. So at this point, we're trying to still visualize by drawing two different graphs. And then in the coming weeks, we're going to kind of get out of the realm where we can visualize everything at once. We can only visualize maybe a piece of it at once.
Got it. So multiple linear regression would normally be like, hey, I want to predict my dog's weight based on its height and its some other variable about
and
the dog.
Breed, and it's
yeah, breed is like a categorical thing, so I want to stay away from that. But like,
I mean, no, but you can have categorical variables in there.
Yeah, and so in this case, even though we still only have two variables of cost and borough, we've now split that into, we've built this model based on cost and I guess in the example that we're looking at, that's Brooklyn compared to Manhattan and Brooklyn compared to Queens. So we've like split this one variable out into two different variables, and now we're doing like a multiple linear regression thing, just like we would do if we were trying to do like dog's weight based on height and breed.
Yeah, this time our predictors are, is it in Manhattan? Yes or no? And is it in Queens? Yes or no? Those are our two predictors for this model. Cool. All right, we ran a little late. I always think like, am I going to have enough to get through an hour? And then we get good questions, so that's awesome. So we will be available on Thursday if you have any questions that you want to ask. Also, there's a really great article and lesson, half a lesson on this in the linear regression course. So you can check those out on Codecademy, and feel free to also post any questions as comments in the YouTube video. Anything I'm missing?
No, that sounds good. Yeah, and then we'll be back next week for another live stream.
Yeah. All right.